Hello and welcome to the third lesson of our NVIDIA Omniverse basic training. This is the third lesson of the basic series. We have another playlist for the introduction series. So in this third lesson, we will explore this Isaac Sim interface. We will build a small robot from scratch. Then we will add physics properties to that robot, and we will be adding joints, articulations, drives, and then we will implement a control for this robot which will allow us to manipulate the robot from the keyboard. Then we will add a couple of sensors, one camera to simulate the RGB sensor and one two-dimension Lidar sensor. And then we will export all the data received from the Lidar sensor into our ROS extension. So we will simulate what would a real robot look from its perspective. So let's go for it. Cool. So in this first module, we are going to navigate through Isaac Sim. Then we will create a few meshes, adding physics to them. We will learn how to organize a hierarchical structure to organize our project in our state. Then we will apply revolute joints to enable wheels movement. We already did a small exercise with that in the introductory video for Isaac Sim. And finally, we will add a drive to simulate the movement of the robot we are creating from scratch. We also did an exercise with that in the introductory video for Isaac Sim, but in this occasion we will do everything from scratch instead of importing an asset from NVIDIA Assets samples. So let's go for it. Okay, I have my Isaac Sim application open. We already had a high-level overview about the interface of Isaac Sim in the introduction video for Isaac Sim. So now let's go and create a mesh. It's going to be a cube. I'm going to change the viewport to Gray Studio. At this moment we don't have physics, we don't have gravity, anything. We just have a visual interpretation of this mesh. So if I click play, nothing happens. So now let's create a physics scene. This will add by default Earth's gravity and other physics to the scene. The gravity is going in the Z direction. You can refer to this axis draw in the bottom left of your viewport to see the direction of the Z, X, Y. Even if we added physics now, if we click play, that is how do we simulate the physical world. Is nothing happening. That's because at this moment this mesh, it is just a visual interpretation of this cube. So now we have to add physics to the cube. Right button, add physics, we add rigid body, then it will be affected by forces like gravity and colliders. The colliders is how objects interact with each other. So we add physics, and now if I click play, it falls and falls and falls because there is no collider in the ground. To be able to see the collider, so the limits of the collision area, if we go to this A here and go to show by type, physics, colliders selected. Now this once we select the cube, this green area, these green lines are the collider's limits. So that's where this object will collide with other objects. Now we are going to add a ground. So create physics ground plane. So even if we have a size for the ground, the colliders expand to the infinite. I'm going to make the ground a little bit bigger. I'm going to select the cube. I'm going to move the cube up. And now I'm going to put the cube in the center. And now if we simulate the physics, the cube falls and stops in the ground. So now we have a world with physics. Okay, now let's go in to give it some... I'm saving the file in every step so I can restart the step one by one. So I'm calling this step number 3. And now we are going to give it some form to the chassis of the robot, and we will be adding 4 wheels. First thing, we are going to move this cube to the center. We are going to change the scale, so 2 in x, 1 in epsilon, and 0.5. I'm going to move it a little bit up. This is going to be the chassis of the robot. Now in the state, right button, create Xform, and we are going to call this Xform, rename simple robot, and pick the chassis and drop in the new Xform. This will create a parent-child relationship. Anything that you modify here will be reflected in the childs. So for example, if I translate the Xform 1 in Z, everything goes up. Let's leave the set local translate set for the chassis in 0. And now we are going to add the wheels. So with a simple robot selected, right click, create mesh cylinder. Let's change the orientation in X, 90 degrees. So we are moving 90 degrees the cylinder. We're going to change the scale to 0.5, 0.75, and no, sorry, 0.75 here and 0.25. And we are going to move the wheel to 0.5, 75, 0.25. That doesn't look too right. I think that one. Okay, yeah, that looks better. Now I'm going to change the name of this mess. Rename. We're going to call it front left wheel. Now with the front left wheel selected, Control D to duplicate it. Let's add the four wheels. We're going to change the names. Rename front right wheel. Rename rear left wheel. Rename that one. Okay, so the front right wheel will be -75 in the epsilon. The rear left wheel we have to move in x will be -0.5, and the rear right wheel will be -0.5 and epsilon -0.75. Okay, and now we are going to give them physics. We select all of them, all the wheels, right button, add physics. We add rigid body with colliders. Okay, and they are marked. So if I click play now, everything falls. Okay, and now we are going to, at this moment, they are separated items. They are not connected ones to each other. Now we are going to connect them. Okay, now let's going to create the joints between the chassis and the wheels. To do so, first select the chassis. It's important to select the chassis before. Then with Control key, select the wheel, right button, create physics, joint, revolute joint. You can see that the joint is not allineated with the wheel and the chassis. So to alienate it, if you selected first the chassis, you will see the chassis path in the body 0 and the wheel in the body 1. Set first thing, we want to rotate in the epsilon axis, and now we are going to rotate. The local rotation for 0 is going to be 0 degrees. Now it is allineated, and then the local rotation for the wheel is going to be -90 degrees. And now we have everything perfectly allineated. If you don't see the sections, go to the A here, then in so by type, physics, select the joint. Then you will be able to see the sections drawn in your viewport. Also, I'm going to remove this thing because it's a bit annoying. So this display, okay. Now we have this. Let's do the same for the other wheels. If you did well, if you click play, it falls, and you can see that now we have a connection between the wheels and the chassis, because the chassis is not falling to the floor. If we check the position now of the not local, well, let's move the robot to the floor so it will not fall. Should be 0.375. Okay, now it's perfectly, the wheels are touching the floor. And now let's go into add movement. We're going to add drive to the rear wheels. So for the rear wheel, right button, add. Right button to the revolution joint. Add physics angular drive. And we are going to add damping. This should be a big number to make it more stable. And target velocity 50. Let's do the same with the other wheel. Add physics angular drive. And now if we click play, it moves. Awesome. You can modify the force here, for example. You can make changes to your variables while the scene is on, so you can see what is happening. And yeah, that's everything for this module. Okay, so now we have finished the module 1, where we created our robot physics body. Now in the module 2, we are going to implement a differential controller using OmniGraph, and this will allow us to manage the movement of the robot. We will configure articulations, so we will improve the relations between the robot and the physical world. We will integrate a keyboard controls, because it's important that we can manage the robot. Then we will analyze the OmniGraph nodes. So we will understand their roles and how through them we control the robot. And finally, we will simulate the robot movement and see if there is any trouble in the way. So let's go for it. Okay, so now we have our robot which move in one direction. Now we are going to add a differential controller to manage our robot's movement. First, we need to add an articulation to our robot. Articulations will allow us to interact with the meshes and joints, making the movements more realistic. So to do so, go to your simple robot, right button. Before that, I'm going to change the name of the joints. I'm going to call that one front, right, and front, left. So then we can recognize the. I also like to. I would also like to organize this in another scope. I'm going to call this joints, and I'm going to move them here. So now I have everything in the same place, all joints together. Now, right button on the simple robot, add physics articulation. And now we are going to add the differential. Going to Tools, Robotics, OmniGraph Controllers, Differential Controller. For the graph path, we leave it as it is. For the robot prim, we add our robot. Well radius is 0.05. Distance between wheels is 1.5. We can see that because if I go to the front wheel, in the X is 0.5 minus is distance 1. Right joint name is that one. Left joint name is that one. We'll leave this at 0 and okay. Now we have created a graphs differential controller here. If 1 second. red button in the differential controller and open graph. We have here the elements of the differential controller. So more important one is on play backtick. This executes this element every frame. So we calculate variables every frame, and well, I don't want to waste time explaining all this, but basically you have control, you can manipulate how do you like it, all these variables. And if you select the differential controller, you have here the variables that are controlling the robot. So now if I click play, nothing happens because we have the desired linear velocity to 0. So basically you can consider that like a percentage of our main velocity saved. If we go positive, go front. If we go negative, go back. Now we are going to add control with a keyboard to our robot. To do so, let's remove the graph that we just created. So delete, and we are going to create a new one. We add our simple robot, select. Before I added one here, but it was 1.5 because the distance must be between left and right, which is 0.75 plus 0.75, so 1.5. Now the right joint, rename, no, that one. Rename. And we select use keyboard control. And these are the keys that we are going to use to manage the robot. Select OK. Now, if we open our differential controller graph, we have many nodes, but the last 4 nodes here are the same as before. If we select the differential controller and we click play, now you can see what is happening here when I go forward, backwards, and when I want to turn the robot. Yeah, in a kind of video game. Yeah. Okay, so now we are going to start the module 3, which is about enhancing our robot with sensors. We will install a RGB sensor. We will be using as well a 2 dimensions Lidar sensor. We will see how to place them in the robot. We will export and analyze the data received from these sensors, and we will see if we face any issue with them. So let's go for it. Okay, first we are going to add to the simple robot an XForm. Create XForm. This XForm will work as a child of simple robot. So when we are moving simple robot, we will be moving the X form as well. We are going to call this X form, rename front sensor, and we are going to put the sensor in the front of the robot. We'll move around. So I guess this is one. So basically now if we move the robot, the sensor move with it because it's a child from the X form of the robot. To put this back. Okay. I'm going to leave this in the center. Let's add rigid body to the sensor. And we're going to create a mesh cube to represent the sensor. Make it smaller. And I'm going to move it here. That in the center. X. Okay, more or less. So now we have our sensor in the front of the robot. So for now it's just a cube. We will add the sensor property now. Now we want to add a camera to simulate a sensor RGB in the cube. First of all, if I click play, you will see that the cube is falling. That's because we don't have colliders here, and even if we had colliders, it will fall somewhere else. So selecting the chassis and the cube with the control key, right button, we are going to create a joint between both of them. Create physics joint, a fixed joint. Now if I click play, the cube is not falling, and if I click play, if I move the robot, the sensor move with the robot. Oh, yeah. Now we are going to add the camera. One thing we need to take in consideration is that cameras cannot be, well, meshes cannot be child of other meshes. So we need to make it child of an X form. So create, wait, come on, camera. The camera is pointing the opposite side. So we're going to selecting the camera, we're going to rotate it, transform in Y minus 90 degrees. And now we are pointing to the front. And the camera position is in the center of this X-form position. So we are going to call this camera, let me have a look. Well, doesn't matter, sensor camera. Now here in the camera item icon, in cameras, you can see that we have our new sensor camera pointed to the front. There is nothing in the horizon. Let's go into add some items around just to see how the camera is looking. Create a cube here. Let's create a sphere here, for example. And now you see that's what the camera is looking at. You can have two viewports, so you can have two different views. So we could go to Windows, Viewport, open the second viewport, and in the left side we have the camera view. On the right side we have the perspective view. I want to remove this information from here. It's a bit annoying. Okay. And if I click play, the camera is not moving. Yes, I want to be sure. Perfect. Now you can navigate. It's a kind of video game. We are not colliding with the message that I just created because they don't have any physics. Well, they have a physics body because they don't have physics. Sorry, they don't have anything. They are just floating images. So so that will represent what is a RGB sensor. Okay. Okay, now we are going to add the 2 dimensions Lidar sensor. To do so, we select the front sensor, X form, then go to create sensors, fix X Lidar, and we select rotating. Now we select the Lidar sensor. Here we have the gizmo of the camera drawn in our scene, but if you don't want to see it, you can just hide it. So I select the Lidar sensor and I'm going to move it to the top of the cube a little bit higher to be sure that we are not detecting the wheels. And if you want to see if the Lidar is working and how it's working, if we go down, scroll down to row, use the properties section, and we select draw lines and draw points, then we click play, you can see the Lidar rotating. It's not detecting anything because the two meshes that I added here doesn't have physical properties. So let's go to add physical properties. to the sphere and the cube physics, we add rigid body with colliders. And now if we click play again, you can see that we are detecting these two assets here. You can, with the Lidar selected, you can lower the rotation rate to see how the Lidar is working more easily. And that's how we added the sensors. In the next module, we will see how to combine this with the ROS2. So let's go to save this file. I'm going to save it as step 9. Okay. And then we will close our application and see you in the next module. Okay, so in this module, you will learn how to stream sensor data from Isaac Sim to ROS2, enabling advanced data processing and visualization. We will set up the ROS2 environment, integrate ROS2 bridge extensions, and configure action graphs to facilitate data streaming. By the end of this module, you will be able to visualize sensor data and RVs and ensure communication between ISAC-SIM and ROS2. So without further ado, let's go for it. So we are going to learn how to stream the Lidar sensor data from ISAC-SIM to ROS2. ROS2 is a middleware framework for building robot applications, enabling communication between sensors, logics, all that in real time. ISAC-SIM has a built-in ROS2 support, and you can run ISAC-SIM ROS2 bridge extension to do so. We will see it in a bit. First of all, you need to install ROS. I have followed this documentation, which link I will share in the description of this video. And I've been following the steps to install ROS2 Humble. Since ROS2 ID developed for Linux and I am using Windows, for this course I need to install WSL2, which is Linux for Windows, basically. And then we will use RVs for 3D visualization. I'm not going to show you how to install all this. You can just follow the steps, and probably I will make another video on how I did that. Or you can just use Linux, Ubuntu, and you can follow the steps to install ROS2 in Ubuntu directly. In any case, it's everything in this documentation. So without further ado, I'm going to, this is my Linux machine already opened, and I need to go to my VS Code. I'm going to open ISAC-SIM, run ISAC-SIM selector, because now I have this already selected, but we need to select the ROS2 bridge extension, and I already installed ROS2 Humble, so we need to select Humble, and then I will launch the application. I'm going to skip this. Okay, now I'm back to my robot. If you go to Windows Extensions and you search for ROS, if everything went well, you will see that you have this extension and this one now active. And this will allow us to use ROS properties within our action graph. Now let's go to configure our action graph. We are going to create a new action graph. Right button, create physics, no physics, visual scripting, action graph. Move it to graphs. And we are going to rename it ROS2 Lidar stream. Right button, open graph. Okay, we are on it. And we are going to add 4 nodes. One is sensor lidar beams. That one. This will read the data from the lidar sensor. Now, this one is to publish the data. This node will synchronize the time in our x-axis with the time in the ROS2, and this one will allow us to execute all this in every frame. So now let's go to connect these things. The tick to that one. Execute. And now we connect every output with every input. Bin temp data. Resolution. I think that's all. And this one we connect the simulation time with the timestamp. Okay, let's go into save that. I'm going to call it step 11. Now with this node, we need to set the target for this node, which is a simple robot, front sensor, the lidar sensor. Select it. And for the output, the information that we are sending to ROS2, we can, in the raw data, we can change the topic name somewhere here, and we are going to call it scan Lidar. This will help us to differentiate multiple sensors in when we want to visualize them in ROS2. Okay, I'm going to save that just in case. And now I'm opening my local Ubuntu machine. First thing we have to do is to run. This is not important, but will allow us to skip some warning message. Then we need to source the humble, and now if you check, we have these two topics, but we don't have our sensor topic yet. That's because we are not running our application. So if we click play and I go back to our Ubuntu, now you can see that we have our topic here. One thing we have to do as well, because this is too slow to represent the data, I'm going to speed up the rotation of the Lidar sensor. No, here. Front sensor, Lidar here. And that's going to put 30 frames. Yeah, very quick. To stop this 1 second, fill, save. And now let's going to run the RVs. RVs2. This will open the application for RVs. This is basically the what our robot will be seeing, but we need to add the LiDAR sensor here by topic, laser scan. Okay. This is okay. This is because we are sending too much information. But if we look around, somewhere should be detecting the maybe I need to change that as well. No, I should be seeing it somewhere. Action graph. I'm not sure if I have to change the name here. Yeah, we need to use the same name. So now we're visualizing the points that is detecting the robot. Let's going to put this a bit on the side. And maybe I'm going to add some more messes. Physics properties, rigid body. Yeah, I'm going to make this one bigger. Now you see. And you can move the robot as well. I want to make this smaller. You remember we have the keyboard keys to move the robot, and the robot stays in the center. We are just moving the world around us. Well, this is how we are communicating. So everything is working fine. And we can avoid collisions with that, for example. I think that's all for this lesson. I hope you enjoy it, and see you in the next one.